Hello physics students. In this video, I'm going to be talking about capacitors again, but this time from the standpoint of circuits, specifically the charge, the current, and the voltage in the capacitor throughout the charging and discharging process. First, we're going to look at the capacitor while it's charging. We're going to talk about all the concepts involved, how these quantities evolve in time, and then I'm going to finish by giving you two equations. One for the charge as a function of time. At any moment, you could calculate exact charge of the capacitor, and the other for the current as a function of time. Again, you could calculate the exact current at any moment in time during the charging process. Then I'm going to do the same for capacitor discharging. So in the end, you're going to have four equations for the charging and discharging of the capacitors. Now, I just want to say, before I jump into the material for today, that in the next video, we're going to be deriving the formulas that I'm just going to give to you in this video. So very exciting video coming where I'm going to use differential equations to actually derive what we're just going to present and use today. So here we are, charging and discharging a capacitor 1. 2 will be the deriving of the formulas that I'm going to write down today. Here's the basic circuit. I've got some voltage source. Remember, we use the Greek letter emph, which means electromotive force. It's like the chemical reactions in a battery that drive current. And I've got a resistor here. Oh, I forgot to label that R. And a capacitor in this kind of, unique circuit with this switch that I don't think we've seen before. This is a switch that can be operated into two different positions. You could switch it up to make this little lever contact point A, or switch it down to contact point B. A will charge, B will discharge, as we'll see. Now, before I go into the concepts, I would like to show you first a capacitor being charged up. You've already seen it before, and I don't have the capacitor with me here, so what I'm going to have to do is use my time machine again to send you back in time to the day when we first started talking about capacitors. I showed you the capacitor being charged in real time with a battery, a switch, capacitor, and a light bulb. So let's go back and take a look so we kind of have a sense of what we're talking about today. Ready? Here we go. I'm going to flip the switch. Okay, so what you should see is that the bulb will turn on just as bright as before, and then it'll slowly dim. Okay, there it is, dimming, dimming, and eventually it's so dim you can't even see it on. Okay, so back again. You saw the capacitor basically filling up. The light bulb was bright in the beginning, and then it gradually dimmed as the capacitor filled up. So what was going on? Well, in the case of charging, the way I change this circuit to charge the capacitor is I switch to position A, and now the loop at time 0, the loop is the battery, the capacitor, and the resistor. This little wire in here is basically hanging there. It's not even part of the circuit, so we just got a simple basic loop with those three components. Initially, which means at time t equals 0, right when that switch contacts point A, the capacitor has no charge. We're starting it with it uncharged, and that means from C equals Q over V, right? This is the basic capacitor formula relationship between charge, voltage, and capacitance. If there's no charge, there must be no voltage in this capacitor. And what that means is there's no restriction to the current. The only voltage in this loop is the battery and the resistor, so the resistor gets the full voltage of that battery. And that means since there's no restriction, the capacitor acts like a simple wire. And therefore, the current is, with Ohm's law, I equals V over R. So that's the initial current the moment that switch contacts point A. However, as time goes on, this capacitor will start building up charge. The plus is coming out of this side of the battery and coming off this end of the capacitor, leaving the capacitor plates like this, plus and minus. Oops. Now, if you think about that, that's creating a voltage driving current this way, the battery's driving it this way. So the capacitor is sort of opposing the voltage of the battery, the voltage of the capacitor. And what that means is the net voltage on the resistor is getting smaller. And so as time increases, the charge increases, the voltage on the capacitor opposing amp increases, and so that drops the current as time increases. And this continues, more and more charge, more and more opposition to the voltage source in the circuit. And eventually what happens when this runs for a long time, after a long time, I put that in quotes, that's actually what the terminology they use in AP curriculum, in the textbooks, but I just want to point out it's in quotes, and so is that as t goes to infinity. I mentioned this during Gauss's law, that the concept of infinity and the concept of a long time is relative. Because some of these circuits reach their end state with like a millionth of a second. So for that circuit, a long time might be like a couple milliseconds, and that's like infinite time. To us, it's like a flash, the capacitor's full. So analogy would be like maybe, I don't know, a dust mite lives like a day or something. To us, a day or a week is not that long to our lifespan, but to the dust mite, a week is like a huge amount of time. So same thing with capacitors. Time itself is, the concept of infinity with time is relative. So we're talking just a lot of time on the scale of the circuit involved. What happens is eventually when this capacitor fills up, the current becomes zero because this capacitor fully opposes the voltage of the battery. In other words, if the battery is 12 volts pushing current this way, the capacitor is 12 volts pushing current the opposite way, making zero current. And then the charge, the final charge on the capacitor, if you use this basic formula and you move C and V together, or M for the voltage of the battery, the final charge on the capacitor is C times M. Now we could represent these concepts, these word concepts, graphically. The charge begins at 0 and rises to C times M. And it would actually look like this if you were to truly graph the charge in a capacitor charging up. And the current, if you were to put an ammeter on a capacitor charging on that little light bulb circuit that I had, you would see the current, if you graphed it, an exponential decay, beginning at M over R, as we said, and gradually decaying to 0. Now, these two formulas are these relationships represented as an equation, a function. And they're very interesting formulas. These show up in differential equations a lot. First of all, the negative exponential is a function that starts at 0. If you plug in times 0, you get e to the 0, and that's 1. So the current starts at M over R, and then as time gets bigger and bigger, e to the negative bigger and bigger number starts from 1 and goes down to 0, like that shape graph like that. And so this goes from 1 to 0 like this, and then M over R just increases the y value, the starting point of the graph. This function, on the other hand, is a really clever function, because e to the negative power, what happens is, as we said, it begins at 1 when you plug in 0, and then as time goes to infinity, it goes to 0. So 1 minus the exponential starts at 1 minus 1, so it starts at 0 instead of starting at 1. And then it decays to 1 minus 0, or 1. So this function begins at 0 and rises to 1 times this. So a brilliant little function that rises instead of decays. Okay? So a couple things about the patterns, and also it rises to this final value. A couple things about the patterns. First of all, the quantity RC we define with the Greek letter tau. You might notice that Greek letter as the torque symbol in mechanics. It's the same Greek letter tau, but we recycle it for R times C, which we call the time constant in capacitor charging and discharging, by the way. And what it does is it comes out when you multiply R times C, it tells you the time scale of how rapidly the capacitor either rises or maybe it takes a long time to rise up, and how rapidly the current drops or maybe it takes a long time to drop. The bigger that RC, that product is, the longer it takes these functions to attain their final values of 0 or C times mth. And it makes sense physically because if you think about it, with a large capacitance, it's like having a large tank to fill. That's what capacitor is. It's a tank that stores charge. The bigger the tank, imagine a garden hose where you're filling a little bucket or filling a swimming pool. The swimming pool is going to take longer, the larger capacitance of the swimming pool. So the bigger C is, the longer it takes this function to reach its final value. The bigger R is, the longer it takes to reach the final value as well. The difference would be, imagine filling the swimming pool with a fire hose, shooting a lot of water, or a little tiny hose that's like a drinking straw in the water. That's going to take longer with more resistance. More resistance also takes longer for this capacitor to saturate up to the final value. So there they are. And I just remembered that you need a pause to catch up and copy these notes down. Okay, so later we're going to do an example problem practicing with these formulas. One final thing I want to point out before I move on to discharging the capacitor is that this is for charge current, but we also can make a formula for the voltage. If we divide both sides by C of this formula, then what happens is this goes away, and this becomes the voltage of the capacitor is the voltage of the battery times that 1 minus exponential function. And so not only does the charge rise up like this, the voltage on the capacitor also rises up to the battery voltage in time. So you can quickly make this into a voltage equation and use that in a problem as well. V equals mth times this term in parentheses. Okay, that's charging the capacitor. Next, what we're going to do is do the same thing, concepts and formulas for discharging a capacitor. But once again, I would like you to see a capacitor discharging. Once again, I don't have one here with me at home. So I'm going to use the time machine again, send you back to the same day where I first charged a capacitor, then I discharged it. So now we're going to watch that same capacitor fully charged by the battery pack that I had on the table. I reconfigure it and I discharge. Let's see how that behaves, and then we're going to talk about the concepts. So, ready? Here we go. I'm going to reconnect the circuit. So now, no more batteries. All we have in the place of the battery is the capacitor, and we've got a loop here. I'm going to flip the switch down, and what we're going to see is that this is going to discharge, and initially the bulb will be as bright as when the batteries ran it. But as time goes on, the brightness diminishes. As the capacitor discharges, unlike the batteries, the voltage is not maintained. Okay, welcome back. So you just saw in the past that the capacitor, when it started full of charge, it was able to make the bulb very bright. That means there was a lot of current in the beginning. And then as the capacitor discharged, the bulb got dimmer and dimmer. You could almost see the exponential decay in the brightness right in that video. So now what we're going to do is summarize those concepts. While you were gone, I was able to update the notes. So here we go. The capacitor is now discharging, and we achieved that by switching to position B at some new time equals 0. So we just reset our timer at time 0. Now, I didn't want to mess with this diagram up here, but basically what we have is this battery is no longer part of the circuit. I could almost erase it, and we just have a simple loop of just the capacitor and the resistor with the capacitor fully charged. So I just kind of threw that sketch in there to remind you that it's only this loop right here, capacitor and resistor. So initially, time t equals 0, the capacitor is fully charged at Q0, whatever charge we started at. And that therefore means that there's an original voltage, because if you've got a charge, you've got to have a voltage for a certain capacitor. So I just solved this for V by moving V over here and dividing by C, and that's the original voltage on the circuit. And that's what drives this current through the resistor, or the light bulb in our case, in the video case, or what we saw in the classroom. We could find the original current because we have a voltage and an R. We can use Ohm's law, V over R, this being the original voltage, that being the resistance, combine the denominators. There, we have an original current that we could use later when we're writing up our functions. However, as this charge comes off the capacitor, the charge immediately goes down. It's depleting, it's discharging. That means the voltage is going down also and depleting, discharging. And that means the current is going down also. Less voltage, less current. So everything is dropping exponentially this time. That continues and continues. But before I move on to that, let me create a pause right here to allow you to catch up copying this down. And of course, you don't need to redraw the diagram. That's already in your notes. All right, so as I said, charge, voltage, current drop continuously. And then after a long time, same comments apply about after a long time being a relative term, t going to infinity, relatively speaking, in terms of the circuit. The charge, the voltage, and the current all reach their final value of 0. The capacitor is fully empty at this point. Now the graphical relationships. Oops, I forgot to update this graph. So the charge begins at Q0 and decays down with time. So there's that graph. And the current, we said, began at this value and decayed to 0. And so we could express those graphical patterns mathematically like this. The charge exponentially decays and the current exponentially decays as well. All these three terms are the original current, which may not be so clear from those values. Coulombs per second. What else did I want to say? Again, we actually have 3 equations, because if we divide both sides by capacitance here, what we have is the original voltage and the voltage at any time. So the voltage decays also. So really the charge equations quickly become voltage by just dividing both sides by C. Same comments apply about RC being able to be defined as the time constant. So if you wanted to, you could rewrite all the formulas with a tau over here, that Greek letter, or RC. Either way is fine, okay? And then, again, same comments about large R and large C. Take more time to empty the capacitor this time. Maybe you don't even need to write these down. It's kind of redundant. All right, so now what I want to do is, what I want to do is first create a pause to allow you to copy this down. Now, moving on, what I want to do is a couple analyses. The first thing that I want to show you is that actually you only need the charge or the current relationship, and you could derive the other. Like, for example, if we have the charge expression for the capacitor when it's charging up, so we can derive the current because we know the current is defined as the derivative of the charge with respect to time. And the charge expression, which I have erased, was the C times M times the 1 minus exponential. I'm going to go ahead and distribute that C times M. So if you look back at your notes, you'll see that this is the same formula with that C times M distributed out. So now I'm going to take the derivative of this expression, and what you could see is that these are just constants. The capacitance, well, that's whatever farads the capacitor is. This is the voltage of battery, which doesn't change. So this becomes 0, that first term. The second term, C times M, are constants. So I can just leave them in front. And then I have to take the derivative of the exponential. And the exponential is a really cool function where the derivative of the exponential is just the exponential. However, that would be true if we had e to the t, then the derivative of that is e to the t. But when we have e to the function, we've got to use the chain rule. So what we have to do is multiply by the derivative of all what's inside the exponential, the derivative with respect to time. So the derivative of negative t over rc with respect to time is just negative 1 over rc. And what happens is this capacitance cancels right here. The negative sign cancels. And what do we get for the current? Mth over R e to the minus t on RC. Hey, that's the other equation. So once again, I'll say it again, you actually don't need to memorize both if you don't want to. You might as well, because this just takes too much time. But technically speaking, you know the charge, you could derive the current. And it turns out that if you wanted to, you could just memorize the current expression. And if you know the current expression, you could derive the charge expression. How? Once again, calculus. So this is how we would do it. Deriving Q from I. Well, if the derivative of charge is the current, the charge is the integral from initial to final of I dt. And so what you would do in this case is integrate from charge 0, because the capacitor is charging, to some Q final of the current right here, dt. And I won't bother solving that out. I just wanted to point out, if you wanted to, go ahead, have fun with the calculus. Integrate this, plug in the limits, and you'll get that 1 minus exponential that I had earlier and I erased. Pretty cool stuff. And the same thing you could do for these equations, just the limits will be different. You'll be integrated from capital Q0 to Q final. All right, so there is one thing. Let me create a pause to allow you to copy this down. One more thing, and maybe I'll go here so I have plenty of room. I want to do an example problem now. Basically applying the formulas that I just wrote down. So let's see. Okay, so maybe what I'll do, so you're not writing while we're solving, I'll create a pause here to allow you to copy this down. All right, so part A, the time for the charge to drop to half the original. So we had 4 equations, Q for charging, Q for discharging, I for charging, I for discharging. Hopefully by the end of today, they'll be in your memory, nice and convenient for you to use at any time. But obviously we're discharging a capacitor, so we're using this formula right here. So let's begin by writing the formula out without any data in it. Standard technique for solving problems. And the original charge was 8 microcoulombs, and we want to find the time for it to become to half its original. So half of 8 is 4 microcoulombs. 8 microcoulombs is the original. E to the minus, the time is what we're solving for. The resistance is 10 ohms and the capacitor is 0.2 farads. So RC will be 10 ohms times 0.2 farads. Okay, so yes, you can plug in charges in terms of microcoulombs. You don't have to convert, because look what happens. The microcoulombs cancel, and if you put in 10 to the minus 6 here to replace the micro, that will cancel also.
You divide both sides by 8, and that gives you 1/2 or 0.5, whatever you'd like, is e to the minus t, and then 10 times 0.2 is 2, and the units of that, seconds. Yes, an ohm times the farad is really a second. There's a way to prove that. We don't want to get into that. So how do we solve for t? What we have to do is take the natural log of both sides to eliminate the exponential. So what we have on this side is log of e to the minus t on 2 seconds, which just turns into negative t on 2 seconds. I'll drop the unit for now. Okay, actually, why not? We'll throw the unit in there. Next thing I'm going to do is take the log of 1/2, put that on a calculator, and I think that's negative 0.63 if I remember correctly. Oh, I don't have it here. Well, I think it's negative 0.63, something like that. I forgot. You know what? Maybe I'll get the calculator out. Log of 0.5, 0.693. All right. Good thing I checked. Okay. So, and that equals negative t over 2 seconds. Multiply the 2 seconds to the other side, and what we get is 1.38. 1.39 seconds, I believe, is the time. All right, well, you could check it on the calculator if you want. So there's the solution. Plug in the charges, divide, and then you've got to take the natural log when solving for t of both sides of the equation. Part B, determine the current at that instant. So B, we have to get the current expression. I equals I0, which is the original charge over RC, e to the minus t on RC. Again, it's a formula that I just erased. Now I just have to plug everything in and churn on a calculator. So I can plug in my Q0, which is 8 microcoulombs. Let's see. Yeah, you know what? I could leave that way. We'll see how if we leave the micro in there. The R is 10 ohms. The C is 0.2 farads. And then log E. E to the minus 1.39 seconds over and that comes out to be, that's going to be 4 microamps. I knew this exponential is 1/2 because of what happened here, right? This has to be this whole exponential plugging in that time 1/2 for this to be true. So I kind of like, that's how I figured that out. Then I just did 8 divided by 2, 4 microamps. And you're welcome, again, to leave it as microamps. Let me create a pause to allow you to copy this down. Okay, so we learned about the concepts behind charging a capacitor, the concepts behind discharging a capacitor. When you're charging, you begin at 0 charge. So we have this kind of rising for Q as a function of time. It rises to its final charge. And then the formula for that, it's in your notes, but it's that 1 minus exponential function. Look at it at the end of this video and try and memorize it. The current formula for charging a capacitor is an exponential decay. So look at that formula, do your best to memorize it. For discharging a capacitor, now what happens is the charge begins like this and goes down instead of like this. It decays, so the formula is a simple exponential decay. And the current also decays, simple exponential decay. So today, we're just learning the formulas, memorizing them, learning how to plug in numbers and solve. Tomorrow, we have a nice, beautiful day where we're going to derive those formulas using differential equations. Great stuff. So I'm looking forward to tomorrow, the next video. I'll see you in that video where we derive these formulas.